Okay, so let's get started with our discussion of Experiment 9. This will be a run-through of the Experiment 9 virtual laboratory for Chem 100. So first and foremost, let's discuss where do we find the Experiment 9 lab pages and Experiment 9 assignments. So you're going to go to the Canvas shell, you're going to scroll down to the Chapter 3 Laboratories, and under the Chapter 3 Laboratory section, we have the Experiment 9 Compounds and Their Bonds lab page. We also have the pre-lab lecture recordings for this laboratory, and we have the Experiment 9 report submission page. I would encourage you to watch the pre-lab lectures, which are a compilation of the lecture recordings from Chapter 2 and Chapter 3. This is a dry lab, which is a much more theory-focused experiment. And so if you need a refresher on the Chapter 2 and Chapter 3 content, I would encourage you to reference those provided videos. This is the Experiment 9 page. There is some recommended reading, and you're going to want to read over the Experiment 9 introduction and procedure pages in your lab manual, and I'll be showing you where to find that momentarily. Now, in this lab page, there is a pretty lengthy introduction section which summarizes the theory behind this experiment and provides a summary of the concepts you'll need to be able to understand and apply to answer the lab questions. I would encourage you to read over the Experiment 9 lab page introduction section, as it has a lot of useful information and a lot of useful examples to help answer the questions in this lab experiment. We, for now, will be scrolling past this introduction, as we'll be expected to read the introduction on our own time, and we're going to focus on, now that we've read the introduction, we've reviewed the chapter, how do we go about completing this experiment? So we're going to go and continue scrolling down past the end of the introduction, and now we're at the laboratory procedure. Before we do anything involving the lab procedure, we need to open up our lab manual. So here is Experiment 9 in the lab manual. We have Experiment 9, Compounds and Their Bonds. It has some lab information, and it provides a summary section. Again, I would recommend reading the introduction summary section for Experiment 9 in your lab manual. Scrolling past this introduction section, we're now ready to look at the experimental procedure. So, where am I going to be putting all of this data, putting all of this information that I'm collecting from the experimental procedure? Well, if you scroll all the way down or continue flipping through your lab manual, you'll reach a section titled Pre-Lab Study Questions, which you'll save and complete alongside this experiment, and the Lab 9 report sheet. This is where you're going to be filling in all of the data and all of your answers for each of the various questions posed in this experiment. So I've taken the liberty of placing the report sheet into a digital format, and we'll be working through this lab together. So whenever I collect a piece of data, I'm going to be writing it down in my report sheet. So let's start now with the experimental protocol and procedure. We'll go through each section, and I'll highlight how to complete each part of the experiment. In some cases, I will complete a representative example and ask you to complete the remaining examples using that guide. Okay, so part A, for each atom or ion, we have to complete the following in the table. So here's part A, here's our table. We're given the name of the element. We're asked to fill in, given the atomic number, the electron configuration, the electron dot symbol, whether it gains or loses electrons during ionization, the electron configuration of the ion, the ion's preferred charge, the ion symbol, and the ion's name. Okay, so they've given us the atomic number. So let's do an example for nitrogen. So nitrogen has an atomic number of 7, which tells us it has 7 total electrons. Additionally, if you check the periodic table, nitrogen is in column group 5A, which tells us nitrogen has 5 valence electrons. We'll use that in a moment. In terms of the electron configuration, we take our standard filling order where we look at the lowest energy orbitals, we fill those first, and we continue filling orbitals until we run out of electrons. So the 1s orbital can hold 2 electrons. The 2s orbital can hold 2 electrons. We still have 3 electrons remaining, and that goes in the 2p orbital, which gives us a 2p3 configuration. Now, we only really care about the valence electrons for the purposes of electron dot symbols. The valence electrons are the electrons in the outermost shells with the largest principal quantum number. So as you can see, we have 5 valence electrons, and thus in our electron dot symbol, we draw nitrogen with 5 dots surrounding it to represent the 5 valence electrons that can be used during ionization or bonding. Okay, so we have the electron dot symbol for nitrogen. Now, in terms of ionization trends, generally for anions, which are formed from non-metals primarily, the preferred charge is the group number -8. This is because atoms prefer to gain or lose electrons to reach an octet or full outermost shell. So in this case, our group number is 5. We subtract out 8, and that gives us a preferred charge of -3. So as we can see here, what this is telling us is in order for nitrogen to get a full outermost shell and generate the nitride ion, which is N3 minus, we would need to go from 5 to 8, which would entail gaining 3 electrons. This ion's charge would be 3 minus, and the symbol would be nitrogen 3 minus. What would the name of this ion be? For anions, they have an ending suffix of IDE. So instead of nitrogen, this would be nitride. So nitride represents N3 minus. So we take this information and we place it into each of the corresponding spots in the table. There's one last thing we have to write out, which is the electron configuration of this ion. So because we've gained 3 electrons, instead of 1s2, 2s2, 2p3, we have gained 3 electrons. 3 plus 3 gives us 2p6. This is a standard noble gas configuration, and thus we can assume that we've calculated this ion's preferred charge properly. Now, one thing to keep in mind, let's look, and I just want to provide a brief comment on aluminum. So aluminum, atomic number 13, aluminum is a 3A element. For cations, which are formed from metals, the preferred charge is the group number. In this case, that would be +3. And generally, metals prefer to lose electrons equal to their group number. So aluminum would lose 3 electrons and generate aluminum 3 plus. I'm going to ask that you write out the configurations for aluminum and aluminum 3 plus independently. One reason I am bringing up this example is that when naming this aluminum ion, you just name it as aluminum. When you are naming and when you're writing out the names for cations, you do not change the suffix. Okay, so for part A, you're going to continue this process and fill out this entire table. Let's move on now to part B. So let's open up part B. There is a display of compounds, and we are going to describe the appearance of sodium chloride, and then we're going to use the internet or a reference to record the density and melting point of sodium chloride. So let's take a look. We don't have a display in the lab manual, so let's go to the lab procedure. Here, we have an image of sodium chloride, and we have some physical property data, such as the density and melting point. So with that, we can transfer that to our lab manual. So sodium chloride appears as a white solid. The description doesn't have to be super detailed, just the superficial appearance. For the density, you can write down the density of 2.16 gram per milliliter. And for the melting point, we have 801 degrees Celsius. Okay, for this second part, we are asked to, for each of these names, write the formula of the positive and negative ion for this ionic compound, and then write the full formula for said ionic compound. Okay, we can do that. So for aluminum oxide, I'm just going to make a note. We have aluminum, which is a 3A element, and oxygen, which is a 6A element. For cations, they prefer to adopt a charge equal to their group number. So aluminum prefers to generate and ionize to yield aluminum 3+, while for oxygen, they prefer to adopt a charge of the group number -8, which would be -2. So oxygen prefers to form the oxide ion, which is O2-. In order to calculate the formula, a fast way to do that is you take the charge for each ion and you cross it into the opposite ion's subscript. So that gives us Al2O3. One thing you do have to check, however, is you need to make sure that this ratio of atoms is the smallest possible ratio. You'll see what I mean in a moment. So we're going to write this formula of Al2O3. Now, calcium sulfide is comprised of calcium 2+ and S2-. And in this case, when we calculate the formula, what we notice is that this ratio of atoms can be simplified. 2 to 2 can be simplified into 1 to 1. And so we write out the formula for calcium sulfide as 1 calcium atom, 1 sulfur atom, because we want the simplest ratio of ions. Okay, so with that example and with that set of examples, you'll complete the remainder of this table. Now, we're going to move to the third part of part B, which concerns the names of ionic compounds. So here we're going to be not only identifying the positive and negative ion, we're also going to write the name. Now, the examples provided all involve main group ions, so you can determine the charge using the periodic table. I'm going to show you another method as well that you'll need to implement for ionic compounds that contain transition metals. Okay, so we have BAF2. So first and foremost, barium is a 2A element. Fluorine is a 7A element. So barium prefers to adopt a 2 plus charge, while fluorine prefers to adopt a minus 1 charge. Where did I get the minus 1 from? 7 minus 8 gives us minus 1. Okay, this is known as the periodic table method. You can also use the formula method, where you have BaF2, you take the subscripts and you cross it up to the corresponding ion's charge. That gives us a predicted charge for barium of 2 plus and a predicted charge for fluoride of minus 1. It's important that you're familiar with both of these methods because there will be cases in which, when you calculate the charge using the formula method, the charge may not be correct upon first calculation. I will show you how to handle that in a relevant example. For now, let's just write out our ion information. And let's write the name of this ionic compound. Naming ionic compounds is relatively straightforward. We write the name of the cation, which is barium. I would double check my spelling on that really quickly. So let me pull up a copy of the periodic table. Spelling is very important in chemistry because even small changes in the name, yeah, so barium needs another letter. So barium. Um, no, I spelled it correctly. Okay, perfect. Always have to check using the periodic table. Now, so we've named our cation. Next, we're going to have to name the anion. So instead of fluorine, we have to modify the suffix to IDE. So fluorine becomes fluoride. So this would be named as barium fluoride. Okay, now let's look at an example where when we try to calculate the charges using the formula method, things get a little bit weird. And in this case, let's look at magnesium oxide. So MgO. So if we were to take the subscripts and cross it up into the charge, we get Mg plus O minus. Now, we know that magnesium is a 2A element, and we know that oxygen is a 6A element. So we'd expect preferred charges of 2 plus for magnesium and 2 minus for oxygen. So the quick way to fix this is just to multiply each of these charges by the same number, which is 2, because 1 times 2 gives us the correct charge of 2. This method may seem redundant for something like magnesium oxide, but this general idea will be applied to calculate the charge for transition metals in transition metal containing compounds. So, for example, magnesium would be Mg2 plus, oxygen would be O2 minus, and this would be named as magnesium oxide. Instead of oxygen, it's named as oxide. Okay, so with this example in mind, you'll complete the rest of this table. So we finished up part B. Let's move on now to part C. So for part C, we're going to read part C in our lab manual, and we have some physical property data that we're going to use. So part C. From the display, we're going to describe the appearance of iron 3 chloride. We're going to record the density and melting point. From the name, we're going to write the positive and negative ions and the correct formula for each compound, and then we're going to name each ionic compound. Okay, so let's pull up our report sheet and let's start with iron 3 chloride. Its appearance is a yellow solid. Okay, as we can see, it's a yellow solid. Has a density of 2.90 gram per mil and a melting point of 306 degrees Celsius. So let's just place that in. As you can notice, it's an ionic compound, so it has a very high melting point. Okay, let's continue on now, and let's take a look at the formula of ionic compounds containing transition metals. Now, the nice thing about transition metal containing compounds is that the ion charge for the transition metal is denoted by a Roman numeral. So for example, in this case, this is iron 2 oxide, and thus the preferred charge would be Fe2 plus. For oxide, we're looking at oxygen, which is a 6A element. 6 minus 8 gives us a preferred charge of -2, or O2 minus. From here, to calculate the formula, we take the charge of each ion and we cross it into the corresponding ion subscript. This gives us Fe2O2. We have to stop here because we can simplify our ratio of ions, and that would give us a 1-to-1 ratio. So this gives us FeO as the full symbol for iron 2 oxide. Now, you may notice for some of these elements and for some of these transition metals, there is no Roman numeral. These are known as fixed charge transition metals. An example would be silver sulfide. Silver is a bit of a unique case in that silver prefers to almost exclusively ionize to form silver plus. For sulfide, that's sulfur, which is a 6A element, and sulfur prefers to adopt a charge of -2. For fixed charge transition metals, you're going to need to know the common fixed charge transition metals and their preferred ionization patterns. For example, silver prefers to adopt a +1 charge, while zinc prefers to adopt a +2 charge. So in this case, if we have silver plus, sulfur 2 minus, and we cross the charge into the corresponding ions subscript, that gives us Ag2S as the formula for silver sulfide. With these examples in mind, you'll complete the remainder of this table. Let's move on now to part 3, where we're asked to provide the ion charge for each cation and anion, and then name each ionic compound. So in this case, let's look at an example here. So Fe2O3. First and foremost, we're going to take each of these subscripts and cross it into the corresponding ion's charge. So we have Fe3 plus and O2 minus. You'll have to check to make sure the anion charge is correct. Oxygen prefers to adopt a -2 charge, so we've calculated the charges of our cation and anion correctly, and we don't need to do any extra multiplication. So our cation in this case is iron 3 plus. The anion is O2 minus. And to name transition metal containing ionic compounds, you write the name of the cation, you put the charge, if it's a transition metal with a variable charge, as a Roman numeral, and then you name the anion. So this would be named as iron 3, so we put the Roman numeral for 3, And then instead of oxygen, it would be named as oxide, just like before. Anions have the IDE suffix for atomic ions. Now, one exception concerns fixed charge transition metals. So, for example, this is a silver containing compound. Silver is a fixed charge transition metal, and as such, you don't need to put a Roman numeral. So, this would be named as silver oxide. You only put the Roman numeral if it's a variable charge transition metal, which is most of the transition metals. Okay, so using these examples in mind, you'll complete the remainder of this table. And with that, we've finished part C. So let's move on to part D. So we're asked to read and complete part D, and we have some physical property data once again. So for part D, we're going to describe the appearance of potassium carbonate, record the density and melting point. We're going to write the name, positive ion, and negative polyatomic ion and the correct formula for each compound. And we're going to write the name of each ionic compound given the formula. So a lot to do, but nothing we can't handle. Okay, so the appearance of potassium carbonate, that looks like a white powder. The density is 2.43 grams per mil, and the melting point is 891 degrees Celsius. Okay, so let's write that down. Okay, so we finished the physical properties section. Now for the theory-focused section, where we have the formulas of ionic compounds. So here, you're going to need to reference a table of polyatomic ions. There's a copy of that in the notes, there's a copy of that in the lab page, and there's a copy of that in the lab manual. You can use whatever reference you prefer. Let me show you what that looks like. So, in that theory section, there has been provided a table of polyatomic ions. I would encourage you to reference this table as it has pretty much all the polyatomic ions we're going to deal with in this course. Okay, now that we know where to find the critical pieces of information that we need, let's continue on and let's work through this part. So, we have our report sheets, and we're asked to deal with sodium nitrate. So sodium is a 1A element, and thus sodium prefers to adopt a +1 charge. Nitrate is a polyatomic ion, which is known as NO3-. To calculate the formula, we can cross the charges into the subscripts. So in this case, that gives us 1 sodium atom and 1 nitrate ion. That gives us, so we have Na plus, NO3 minus, and a full formula of NaNO3. Now, there may be cases in which you have a variable amount of the polyatomic ion. For example, looking at chromium 3 hydroxide, well, we see the Roman numeral 3. That tells us chromium has a 3+ charge. Hydroxide is OH minus. So we take the charge and we cross it into the corresponding subscript. And that gives us a formula of 1 chromium atom and 3 hydroxide ions. You have to use the parentheses and a subscript to denote if you have multiple units of a polyatomic ion. So we have 3 hydroxide ions, and that's why we have a parentheses around hydroxide and a subscript of 3. So with that example, you'll complete the remainder of this table. Let's move on to the next part. Names of ionic compounds. So here we're given the formula. We're asked to write out the cation and anion and then name it. So looking at this first case, we have aluminum. So aluminum is a 3A element, so it prefers to adopt a 3 plus charge. Nitrate is NO3 minus. We can also calculate the charges using the subscript rule, where we take the subscript and we cross it up into the corresponding ion's charge. That gives us aluminum 3 plus and NO3 minus. The methods yield the same result, so this tells us that we've done something correctly. Okay, so we have aluminum 3 plus, we have nitrate, which is NO3 minus, and so to name these polyatomic ion-containing compounds, you name the cation, and then you name the anion. You don't adjust the anion suffix for polyatomic ions. So this would be named as aluminum, and then we name NO3 minus as nitrate. So you just write the name of each ion in order. So with that example in mind, you'll complete the remainder of this table. From here now, let's move on to part E, and let's read the instructions for part E. So, taking a look at part E, in the lab page, we have to read and complete this part, and we have some physical property data. Okay, so for part E, we're going to describe the appearance of water. We're going to write the name and formula of the molecular compound, and we're going to provide the names for various molecular compounds. Okay, let's start with the physical property data for water. Water is a clear liquid. The density is about 1 gram per milliliter, and its melting point is 0 degrees Celsius. As you notice, covalent compounds generally have lower melting points. Okay. Okay, let's move to the next part. We are given the name for the molecular compound, and we're asked to write the formula. From here, you're going to have to be familiar with the naming prefixes. So di, tri, tetra, penta, etc. So there's a table of prefixes found in the lab manual and in the introduction section of this laboratory. Let me show you where that is, just so that way we're all clear on where to find the information that we need. So here's a table of prefixes. I would encourage you to reference it throughout this experiment. Okay, dinitrogen pentoxide. So first we have nitrogen. The di prefix tells us we have 2. Pentoxide, that tells us we have an oxygen atom, and we have 5 of them. Pent corresponds to 5, di corresponds to 2. With this example in mind, please complete the remainder of this table independently. For this next part, we're going to name some molecular compounds. So for naming molecular compounds, you're going to write the name of the first atom in the formula, along with a prefix if there is more than one. Then you're going to write the name of the second element, including a prefix, and adjust the suffix to IDE. So for example, in this case, we'd name this first compound as chlorine. We write the name of our first element. No prefix needed because we just have one chlorine atom. There are 5 fluorine atoms, so we'd use the pent prefix. So this would be chlorine pentafluoride. Remember to adjust the suffix of the second atom to IDE. So, with this example in mind, you're going to complete the remainder of this table. It's important to double check your spelling. because even small changes in how you spell the names in this formula can indicate entirely different compounds. Okay, we're now going to move on to part F, which is detailed in your lab manual. So if you have a molecular model kit of your own, I would encourage you to use it, but you don't necessarily need it to complete this part. So here you're going to draw the electron dot formula. You're going to count the electron groups around the central atom. Use VESPR to determine the electron group arrangement. You're going to identify the molecular shape and indicate if the molecule would be polar or non-polar. That's a lot to unpack. There are some rules for writing Lewis structures that I provided in the lab manual, and there are some rules for determining molecular geometry as well as electron pair geometry, and some rules for calculating polarity along with some examples. I would encourage you to read those examples as they provide a lot of very useful information in terms of drawing Lewis structures and interpreting Lewis structures. To show an example, I'm going to pick not water because that's already shown in the pre-lab reading. Let's look at sulfur difluoride. And let's do a full run through of how you'd answer this question. So the first thing you do when you're making a Lewis structure is you count valence electrons. So sulfur is a 6A element, so it has 6 valence electrons. Fluorine is a 7A element, so it has 7 valence electrons. We have 2 fluorines, so that gives us 6 plus 14, which gives us 20 valence electrons to work with. Next, we place the least electronegative non-hydrogen atom as our central atom. That's going to be sulfur. The fluorines are placed around sulfur. Remember, you can only put a maximum of 4 atoms around a central atom due to the octet rule, at least for the purposes of this class. We're then going to form one bond each. That uses up 2 electrons per bond. We have 2 bonds, so we subtract 2 times 2, or 4, and we have 16 electrons remaining. From here, we're going to place valence electrons on the outermost atoms until they have a complete octet. 2, 4, 6, 8. 8 electrons in total. We've used up 6 electrons. We have 10 electrons remaining. We repeat that process for the second fluorine. So that's 6 electrons again. We have 4 electrons remaining. Sulfur has an incomplete octet. So we add 4 electrons to sulfur. We've run out of electrons, but as you can see, fluorine has a complete octet, sulfur has a complete octet, fluorine has a complete octet. Wonderful. So we have the full electron dot formula. Now let's interpret this. So an electron group is equal to the number of bonds plus the number of lone pairs. When you're determining the electron group and the electron pair geometry, we are focused on the central atom or atoms. In this case, all of the formulas have just a single central atom. So looking at sulfur, we see we have 1, 2 bonded atoms. Let me rewrite this number of bonds to number of bonded atoms, as that's a little bit more accurate for this particular calculation. So in this case, we have 2 bonded atoms, 1, 2 fluorine atoms, plus 1, 2 lone pairs. That gives us 4 electron groups. 4 electron groups corresponds to a tetrahedral electron pair geometry. Now, in terms of the shape, when we're figuring out the shape, we see that we have 2 lone pairs and we have 2 bonded atoms. When you have two lone pairs and two bonded atoms, this tells us we have a bent geometry. Now, because this molecule contains polar bonds, there is a net bond dipole. And because the central atom has a lone pair, and in turn, because this geometry is not symmetrical, these bond dipoles do not cancel, and this overall molecule would be considered polar. Generally, in terms of polarity, if your central atom is bonded to multiple different atoms, or if it contains a lone pair that makes the geometry asymmetrical, your molecule would be considered polar. So with this example for sulfur difluoride in mind, I'd like you to complete the remainder of this table. So with that, we provided a full run through of experiment 9. Once you complete this experiment, you'll submit it at the experiment 9 report submission page on Canvas.